Welcome back, everyone. I hope reading 2.8 wasn't too abstract and math theory heavy for you to get something out of it. I know that there were some sort of technical proofs and theorems in that section, and I know we're sort of jumping around the book, but I think this section is important, and I think it also fits well right here in our sort of discussion. So I hope everyone got something out of it. I just sent out an announcement about 30 minutes ago, saying that I'm pushing back homeworks 2 and onward. I think about 3 days for each of them. Um, I realized that the time between homework 1 and homework 2 was only 3 days, and I didn't think that was reasonable. Thinking about it right now, so I opted to push the due dates back for everything. I think this gives us a little more breathing room between topics in class and their kind of homework due date. But I am a little worried that it kind of congests the back half of the course with stuff to do and turn in. So I'd encourage you to still download your homeworks early and look at them as soon as they're posted and think about them and even start working on them as soon as you can. I'm going to try to keep. I'm hoping to. Correction. I'm planning to post details on the project tonight, and then I'll talk about it more in class tomorrow, and then post the homework 3 tomorrow night. Is my current plan. Also, tomorrow is one of our scheduled question catch-up days. Um, there's a little bit of graph theory stuff that I didn't get around to talking about. So I'm going to start off going over that, and then I'm going to leave it to you guys for questions. I've posted a Piazza question that you should be able to respond to if you have any specific questions in the book or anywhere else really that you want me to talk about, or if you want a refresher on some linear algebra topics. Unfortunately, I can't go over the solutions for the homework 1 just yet because we have a few people who got extensions, had computer problems in a different time zone, we're traveling, that sort of thing. So, but as soon as that's over, I'll post the solution key and we can talk about that. I think that's all the announcements I had. So homework 2 is now due next Monday instead of this coming Friday. So that's the 18th instead of the 15th. And I think someone asked me if it was, I may have had listed somewhere that it was due the 12th. It is due the 18th as of 35 minutes ago or so. So let's move into the topic, the material for today. Convex analysis. This is just the study of convex sets, and it's important for solving problems, linear problems, convex nonlinear problems, all sorts of things. We're just going to cover some of the basics because that's all we need for linear problems. If you take DOR2, we'll talk a little more in depth about different types of convexity and different types of sets. But for now, we'll just define what a convex set is. So start with sets. A set is just a collection of things in math. Typically, a set is denoted with a curly brace if it's a discrete set, so if it's got discrete things in it, like I've done for our indices for different constraints. We could also have a discrete set of points in space. So those are points in 2 dimensions, like we've done in high school, plotting functions and things. You can also, a little more abstractly, have a set of functions in a sort of function space. So this is set builder notation for the set of quadratic polynomials. So degree 2 polynomials. Which is, if you don't understand what you're looking at here with this set builder notation, this just means the set of all functions ax squared plus bx plus c such that a, b, and c are real numbers. We are not going to do anything with the set of quadratic equations, but I thought it might be fun to show you that you can do that. So we call a set, oh well, you can also have a set that is a region, right? A region in R2. Which is sort of what we'll be dealing with in our attempts to solve linear programs. We call a set convex if for any 2 elements of that set, elements just being points or functions or whatever, pieces of that set, for any 2 elements of that set, we can draw a straight line between those 2 points, and that whole line is within the set. Every point on that line is in the set. That's sort of the basic understanding. The more abstract theoretical understanding, so we call it convex combination. This is just a generalization of a line segment between 2 points in space or in any other set. The reason we use this definition is just because you can't draw a line between 2 polynomials or some of the more abstract sets. A line segment is not something that's easy to define, whereas a convex combination is generally not problematic. But for the purpose of our class, you need to understand this part. So sort of more grounded. Can I draw a line between 2 points, any 2 points in the set, without leaving the set? So this figure comes from the book. Right, I'd drawn a line on this one. We can see that it's convex. Any 2 points we draw, we can have a line between them. 2 is not convex because there's a big hole in the middle, and I can imagine drawing a line that crosses that hole. Very similarly for 4 here, there's a gap. For 3, it's a cube. The volume of the cube is the set, so you can pick points in there. Think about it in your brain. Think about drawing lines between any 2 points in that, and you'll quickly see that you probably can't leave the set with that kind of technique. So these 2 are convex, and these 2 are non-convex. Great. So I'm going to open up a poll real quick, and we'll We'll run through a few examples, and you guys are going to tell me whether you think they're convex or not. We're going to start with the set of real numbers. So this is just a number line. Say we have 0 here, 1 here, -1, 2, -2, going on to infinity in either direction. Is that one convex or not? What do you guys think? Great. Seen a lot of yeses. Here we go. Now we're heating up. Good, good, good. The real numbers, the number line, is in fact convex. If I have 2 points, x1 and x2, the line between them is just the number line. So it's still in our set of real numbers. If we want to think about the convex combination, say we have x1 is -1.5 and x2 here. x2 is positive 1.5. The convex combination, let's say lambda equals 1/2. I've just set myself up for having to do some on-the-fly division. So that's going to be 0.5 times -1.5 plus 0.5 times 1.5 is -0.75 plus 0.75 is 0. And you'll find that if you exchange the lambda for any other point between 0 and 1, you'll come up with another real number on this sort of line between x1 and x2. Sure, so you have a question when you're done. Okay, sure.
So not exactly about this exact topic,
Yep.
but I have so about like doing Python. I was wondering if you could make like a cheat sheet of commands, kind of, because like for me personally, I'm just now learning Python. I've learned like C++ and
Right.
JavaScript and stuff like that, but I feel like that would be helpful. I just wanted to ask that before I completely forgot.
That's a good idea. I'll see what I can throw together.
Thank you.
All right. Well, let's move on to the next example. I should write yes here. And that poll. Relaunch the poll. Move on. Let's. What about a plane in R2, or as we'll talk about later, a hyperplane. Uh, these are all sort of the same class of object. It's a yeses again. So again, the answer is yes. So this is just a generalization of what we just did, sort of. Um, if we have any 2 points in this plane, we can draw a line between them without leaving the. Specifically, we can draw a straight line between them without leaving the plane. Even if this plane were sort of tilted up in R3, somewhere, we can draw the line between them. Whether or not they expand to infinity, right? Yeah. Great. End poll. Relaunch poll. What about this? What about the union of two convex sets? So the union is going to be everything that is in that is in either set. So this purple almost outlines the union. Is this one convex? Wait, did that poll launch?
Yeah, it launched.
There we go. Great. All right. I'm seeing mostly no's. The answer is no. It's not convex. If we have these 2 points, for example, we draw the straight line between them. Let me use a different color just to be a little. That doesn't show up. All of this section of the line is outside the set. So this is not convex. And this is true in general for two convex sets. The union may not be convex. Relaunch the poll. What about the intersection of two sets? So this is all the points that are in both sets simultaneously. So if I try to highlight where that is, it's sort of the middle of the Venn diagram. Getting yeses. Good. So the book actually proved this, but the intersection of two convex sets, of any two convex sets, is convex. So that's good. And we'll be using this particular piece of information. We'll be relying on it quite heavily coming up. A few more times here. We got a tricky one, I think, coming up. What about the set of integer points in a space? So this is a 2D, so this is z2. So this is, say, this is 0, 0. This is 1, 1. This is 0, 2. This is, x, x, or xy integers. No, not convex. That's most of the answers we're getting. So why is that? Well, we have two points. Let's pick 2 points and draw the line between them. Sure, in this case we have this point. That point is in the set. But we also have these points on that line, which are not in the set. We have to remember that every point on that line segment must be in the set. So no, not convex. What about a curve in Rn? So the set we're interested in is the surface of the curve itself. Good. Mostly no's. Few yeses. Well, let's think about it. Let's pick 2 points. I'm going to pick maybe the obvious points. The two peaks of this sort of, I think this is some kind of cosine. The two local maxima, and let's draw the line between them. That line is not on the surface of this curve at any point. So no, it's not convex. What about, I think this is my last one for this section. What about half of R2? Or in fact, any real number space. Lots of yeses. Yeah, so let's think about this. Let's pick S. Let's pick some random points. Yeah, we can draw that line. Let's pick 2 points on the edge. We can draw this line. Pretend that's all in the set. Let's think about how we might draw a line that leaves the set. Let's say we have a point in the set. We want to draw a line that leaves the set. Pretend that this expands on to infinity, sort of in all these other directions. We want to draw a line that leaves the set, but the point we have to get to is going to be outside the set, right? If ever we want to leave the set. So, no. Well, so yes, this is convex. Because we can't draw a line segment outside of the set without having its endpoint be outside of the set. That may have been a confusing way to make that statement. But every pair of points in the set, its line segment, its convex combination lies also in the set. So this is important for us. So great. So let's define hyperplanes and half spaces. The book does a job of this. It defines it, but I don't know that it gives a great kind of intuitive explanation of what they are. So a hyperplane is just the generalization of a line to however many dimensions of space you want. So this is the format that the book gives, and it's a good format if you're familiar with set builder notation. This just says any vector in let me try that again. Any vector x such that A transpose x equals B. And you may remember from our modeling discussions that Ax equals B is a linear function. So a hyperplane is just the set of points that lie on that are valid to lie on a linear function in however many dimensions. We can see in R2 that our arrow here is a linear function, and in R2 a hyperplane is just a line. A half space is the generalization of linear inequalities to however many dimensions. The only difference between these two notations is that we have an inequality here. So anything for which any vector x, any point x in Rn, for which Ax or A transpose x is less than or equal to b, is valid to that inequality, is part of our half space.
Will it never be greater than or equal to?
It can be greater than or equal to,
Okay.
but remember that if we multiply by -1 to either side, we can flip the inequality arbitrarily between less than or equal to and greater than or equal to. So different books will pick different standards for which inequality they want to show, but just know that they're effectively interchangeable just by multiplying by -1. Well, let me write that a little more clearly, perhaps. So this is equal to the set of all x in Rn such that -1 times A transpose x is greater than or equal to b. Correction. -1 times b. So those are the same set, and they're both convex, and they're both half spaces. So if we think about the models we've made, our linear programs, all of our linear constraints are half spaces, unless they're an equality constraint, in which case they're just a hyperplane. Our half spaces, we've decided that half spaces are convex, and the book has a fun short proof for why the intersection of convex sets is itself convex. And we've also shown that sort of above. So given all of this information, we know that our feasible regions are convex for LPs. The feasible regions of LPs are always convex, which will be very, very important for solving these things. The technical term for the intersection of multiple half spaces is a polyhedron. The plural is, of course, polyhedra. So the feasible region of every LP is a polyhedron. And all polyhedrons, all polyhedra are convex. So all polyhedra are convex. Now, integer programs are not convex. Why is that? Their feasible regions are not convex. Well, if you remember, we decided that the lattice of integers is not convex. An IP will have a polyhedron, what have you, sort of superimposed over the lattice of integer points. And we're going to take the intersection of those, which gives us sort of these distinct points. And that's pretty obviously not convex. I'm drawing a line between those 2 points. It's not in this set. So IPs are not convex. Late in the class, we'll talk about we'll talk a little bit about how IPs are solved and how we get around this non-convexity issue. A very important aspect of polyhedra and convex sets in general is that they have extreme points. So an extreme point is a point in a set which cannot be expressed as the convex combination of other points in the set. Maybe the more grounded and reasonable way to say that for our purposes is that extreme points do not lie on the line segment between any 2 points in the set. So most of the points in our convex set can be expressed as parts of a line between 2 other points. Extreme points are the exception. They're the points that cannot be expressed this way. That's their definition. And we'll talk about what that means. But first, we have a few more polls. We'll let you guys think about whether some of these points are extreme. Is this an extreme point to the blue set that we have here? Can this be written as a convex combination of 2 points? Is it on a line between 2 points that are in the set? Okay. A few no's, but mostly yeses. Let's think about this. Let's try to draw this as a part of a line between 2 points in the set. If we just draw a line through it, neither endpoint of this line is in this set. If we draw this line, this endpoint is in the set, but this endpoint is not. Again,
So I have a question.
yes?
So see, I was going to put no because I was a little bit confused. But
Sure.
if you had the point inside of the plane, right? Do the segments themselves constrain how far out you can make a point?
So
Like,
you mean is this point on the set?
no, so like if you were to put a point in the middle of the plane,
Sure. Let me get a different
if
color that will show up.
like you can't just make any size line, like you can only go as far out as the line segments constrain you to. Because you see what I'm saying? Because like you could still technically go outside of the line segment.
Um, if I draw a segment from this point over here,
Right. Like you can't do that, right? Or
um, right. So the line segment is strictly between 2 points. It doesn't expand beyond it. So if we wanted to draw a line segment that is outside of our set, that extends beyond our set, the endpoint is going to be outside of the set.
Like,
which does not apply to our definition of convex. So if you're thinking about whether or not something is convex, the 2 points need to be inside the set, um, or on the boundary perhaps, and
well,
the
maybe I didn't like explain
the
the
line
question.
segment is strictly between those two.
Yeah, so let's just say like the middle orange one that you drew at first, right?
Sure.
So let's just say that that is our extreme point. Like that is
Is this one
the
an extreme
example.
point?
Right. So like if you drew a line segment from that point, let's just say through that one, and only went from the left line segment to the right one.
From this to this?
Yes. Like you can't make a line segment that goes outside of that constraint, correct?
Right.
Okay, gotcha.
And uh, so if we think about this point as well, this is not actually in the set, because it is sort of beyond one of our other constraints.
Gotcha.
Right. Excellent question. So this is extreme. Uh, yes, any line segment we try to draw through this point has at least one of its endpoints outside of the set. And remember that these line segments have to be straight, so I can't draw sort of an angled thing to get around this. What about this one? Okay, mostly no's, a few yeses. Let's what about these 2 points? Our sort of questionable point lies on the line between those two, right? And because our inequalities, our LPs, are less than or equal to or greater than or equal to, they're not strict. These points on the boundary are in fact in the set. So no, this is not extreme. I know this is a little confusing because before we were asking, um, using our points as endpoints, can we draw a line? Here we want to ask, can this be a midpoint between 2 points? So no, this is not extreme. Uh, what about this one? Again, we're on the integer lattice. Pick some points. Any point on the integer lattice. So this is a sort of a tricky one, and it challenges the definition I've given so far. Because we can draw a line with that as its midpoint, or as yeah, the, with that point on the line somewhere. We can do that. So in that sort of respect, it looks like it is extreme. But the rest of this line is not in the set. So we've already decided this set is not convex. Hmm. Like, I didn't really give this one as much thought as I should have while I was preparing this. This is interesting. Let me look up the exact definition in the book real quick. Where did I put my book? I'm tempted to say that this depends sort of on some extra context. C is not an extreme point of C if and only if it can be written as the convex combination of 2 points in the set. However, the book does say that the set should be convex. The set in question. So yes and no. It's going to depend on sort of the context of the question, of the problem. It is extreme. I always misspell that. To the set, but the set is not convex, and extreme points are poorly defined. On non-convex sets. That's my official statement on the matter. Excellent. Good to challenge what I thought was the answer was. Come up with some new ideas. And the poll. I didn't want to do that. Wrong button. I think I have. Yeah. Is this point extreme? I think we're going to have the same sort of issue, right? Because this set we've already decided is not convex. I didn't think about this. This is fun. Fortunately, we won't have to deal with these kinds of questions for the rest of this class because we'll be using convex sets with linear objective functions. But this is interesting, I think. Yes and no again. For the same reasons. It can't be written as a linear combination of points in the set, but also the set is not convex. So there are, yeah. Now the book also tells us, I need to add a page here. The book tells us that if we have a set that looks something like this. Um, our extreme points for this set are these 2 points, or these 3 points on the line, but also everything on this curve is also extreme. Now we won't be having curved constraints for our problem, so this is not a polyhedron, but it is convex, and so we can define extreme points on this set. And maybe I should have included that in our polls. Yes, so all the red sort of markings are extreme. In fact, the book gives an example of just not quite a circle, but an entirely curved boundary sort of region, and the entire boundary is extreme. So good. So what is the purpose of an extreme point? Why do we care whether a point is extreme or not? Well, let's think about our polyhedron. Actually, I'm going to do this slide later. Let's think about our LP. Say that this is the blue is our feasible region, and the green is a level set of our objective function. So this is if z is our objective value, then this line, this green line, is all the points for which z equals some number. I'm just going to arbitrarily pick 10. That's what that green line represents. So for every solution on this line in our feasible region, the objective function value is 10. And let's say we're trying to maximize. And let's say that this is the level set for z equals 11. Because this is a linear function, our objective function is linear, we can kind of continue to extrapolate level sets. And we can see that we intersect, as we continue to increase z, the last point we intersect with in our feasible region is extreme. And if we were to try to draw any more level sets, any larger ones, z equals 14 maybe, that doesn't intersect with our feasible region at all, right? So this point is our optimal solution. Have I made that clear to everyone? Is that explanation trickling down, coming through clear?
So the max is going to be the z equals 12.5. Like that's what you would be looking for. Like I always look at the examples and try to find out, you know, where the answer to the question is at, and by just showing the I understand where the optimal solution is at, but how would you define it versus just writing the lines on the graph, if that makes sense?
Right. So that is the question. That's the big question. How do we find this point without just scanning through our feasible region and assigning values to things? Um, and we'll talk about that at length in this class. I think you're trying to get to how do we actually solve LPs, and we'll get there. But you're right, this is not the way we would really go about it. This is just me trying to show you um, and show you an important piece of information, right? That important piece of information is if an LP has an optimal solution, one of the extreme points will be optimal. This is a little confusing, this statement. But first, it's important to realize that not every LP has an optimal solution, a best solution, you might say. Not every LP has an optimal solution, and we'll talk more about that coming up in, I think, the next lecture. But if it does, if it does, one of the extreme points will be optimal. It may not be the only optimal solution, but one of the extreme points will be an optimal solution. Does what I'm saying make sense? Can you see how that might be true from our sort of argument about level sets? And just let's see what happens if we try to minimize. So this is z equals 9, z equals 8. Uh-oh. Z equals 7 is our last sort of feasible level set, and it intersects this point, that extreme point. And we'll talk more about what different classes of solution an LP could have in the next lecture. But this is the important aspect. This is what this whole lecture is built up to. If the LP has an optimal solution, one of its extreme points is optimal. This is huge because it means that the only thing we have to do to solve this problem is find all of the extreme points and compare them, right? That's all we need to do. If we can do that, we can solve these problems. The problem is there might be many, many, many extreme points to a problem. Let's go back to that slide I skipped earlier and talk about why that is. So an n-dimensional polyhedron, for in n dimensions, a polyhedron has an extreme point wherever n of our boundary hyperplanes intersect. Wherever n of our constraints intersect each other. at equality. So if we have m constraints, our LP could have as many as m choose n extreme points. And if you haven't had probability or combinatorics or something else like that, m choose n is very, very large, potentially. For a bigger problem, if you have 10,000 constraints, um, you could have far too many for a computer to enumerate and compare in anyone's lifetime. So this is not really a good way of finding our optimal extreme point. We know that we only need to look at extreme points, but we still need to figure out a way to be clever about which extreme points we look at. And so that's going to be finding out that trick is going to be sort of the next arc of this class. How do we navigate our extreme points cleverly? So that's all the material I have for today. I just want to reiterate that I sent an announcement before class that the homeworks, the future homeworks, not homework 1, its due date is still yesterday, unless you have an extension from me. The rest of the homeworks have all been pushed back. I think usually it's a 3-day pushback. So homework 2 is due on July 18th, at least on this side of the international date line. Yeah, so tomorrow is a question/catch-up day. I've posted a Piazza forum sort of question. If you have any specific questions in the book, any exercises in the book you want me to go over, or exercises from anywhere else, drop those in that Piazza forum, and I'll try to work those in to our discussion tomorrow. Also, I'm planning on uploading the details of the project tonight, so be on the lookout for that. Other than that, I'm going to stick around for any questions anyone might have, but other than that, you guys are free to go.
How you doing?
Doing well. How about yourself?
Good. Um, so what time are your office hours again?
4 to 6 are my scheduled ones.
And you're doing Wednesday, Thursday, Friday, correct?
I think it's Monday, Wednesday, Saturday,
Okay.
and the TA is doing Tuesday, Thursday.
And what time is his?
Um, 11 to 1, so shortly
Okay.
after class.
Okay. Um, so I'm gonna be honest, I struggled like this this first homework, it
Yeah,
got me. And and I don't and I like don't uh I don't blame like the teaching or any of that type of sort. I think it was like my own because I'm now having to do 3 more classes than what I was doing.
oh yeah?
and it kind of like I'm doing five total, so it kind of
This
like
semester.
yeah.
Oof.
And so I've been doing an English and an ethics since right after spring, and now I'm getting into tech. So this is like my first time taking tech classes.
Yeah.
Um, and so I think it all kind of just like hit me at once. But um, I'm just like, I guess